Okay, I'd like to welcome you to this colloquium from the Department of Computer Science and Engineering. Today I'm happy to introduce Mike Burrows, who's visiting from Compaq System Research Center in Palo Alto, formerly Digital's System Research Center. Mike did his PhD at Cambridge University in England and has been at CERC for about 10 years, where he's done a lot of really outstanding work in operating systems, spanning quite a broad range of activities, including security. And today he's going to talk about indexing.
Thank you. So you'll notice that the title on this slide isn't quite the title that was distributed. And the only reason that the title that was distributed was different is that Hank thought that more of you would come if there was AltaVista in the title. But the content hasn't changed. So I'm going to tell you about a library for indexing and querying text, which did happen to get used in a major web search engine. So when I wrote the library, I didn't have web search in mind. So one of the goals was that this library be a general purpose thing, that it should provide good query performance. It should scale quite a bit. I wanted to index things up to a few hundred gigabytes. I wanted the index to be reasonably small. The main reason for that is that if you make your index bigger, you have to transfer your index into your RAM and then into your cache in order to do anything with it, so it's slower if you make it bigger. I wanted to ensure that it was possible to do a query at any time, even if you were in the middle of doing an update. The only reason that that was a hot button for me was that in the last indexer I'd written, I'd made that mistake. And I wanted the update performance to be reasonable, but I didn't care very much about it. There were some things that I did not care about. I didn't care about it scaling beyond a terabyte of text. And there were things that are not in this library. It doesn't parse documents. That's done by another library. It doesn't parse queries. That's done by another library. It doesn't do ranking that one would normally associate with information retrieval, things like collection frequency weighting. That's done, again, by another library. So this is a fairly low-level indexing library. What it does is basically gives you inverted files and the ability to query them really rapidly. So I'm going to tell you just a couple of things about this library that are different from some other indexing systems. I've actually cut a little bit out of this talk in order to make room for some more war story-like things at the end, which you might enjoy. But first of all, let me talk about inverted files. So I chose to use flat inverted files that map words onto list of locations. Words, as far as this library are concerned, are null-terminated byte strings. There's no interpretation on those words whatsoever beyond those. Locations are 64-bit integers. Again, it's a flat 64-bit space. There's no interpretation on what those integers mean. The client gets to decide what those locations mean. So there's no predefined notion of document boundaries or word numbers or anything like that. You can choose to lay out the documents within that location space any way you want. It is not the case that you look something up in this index and it gives you back a pair, like a document number and a position within the document. It just gives you back one number. So how do you encode documents on top of this location space? There are some constraints. A document has to be a contiguous range of numbers in location space. Documents do not overlap. Location space is allocated densely. So the first document starts at location 1, and the second document starts where the first document stops. There is a word with a funny spelling, which I call the ndoc word, and the indexing library guarantees that that word is indexed at the last location in every document. Every piece of document structure, including where the ends of the documents are, is encoded as words. So if, for example, you wanted to specify where there was a title field within a document, the way you would do that is you would invent two words, probably with funny spellings so they wouldn't conflict with normal words. One of those words would stand for the beginning of a title, and one would stand for the end of a title. And then you'd put those into the two places in location space where you wanted the title field to be. So everything is done with words. The indexing library doesn't have to deal with anything else. So this number line you see at the bottom here is meant to represent location space. It just starts at 1 and keeps going up, and documents occupy subranges of it, and they are densely packed. So within the inverted file itself that stores the index entries, the words are ordered lexicographically. That's just so you can find them more easily by being able to do binary search. And each word is followed by a list of locations. So the way to think of this is if you're not familiar with inverted files, is it's just like the index that you would find at the back of a large book. So there's a list of words, they're in alphabetical order, and against every word there is a list of locations. At the back of a book, those list of locations will be page numbers. Here, they are just these locations that I've been talking about, and it is conventional in many clients of this library to use those locations as word position numbers. So you just start counting the words and keep counting up. There are two types of compression used in the inverted file format. One of them is irrelevant, and the other one is relevant. I had thought that the irrelevant one would be relevant for some applications. I have not yet found one, but I'll tell you about it anyway. Common word prefixes are compressed. So if, for example, you had the word wombat, and then the next word in the index was wombats, then the index would not bother to store the wombat part of wombats. It would just say 6 characters are the same, and then there's an S. This doesn't save you anything with any of the applications that I've used. But I thought that there might one day be such an application with skewed statistics where it would be useful, so I put it in, and it doesn't cost you much. The interesting compression that's here is delta compression on the lists of locations. All those lists of locations are stored in monotonically increasing order. So it's very easy to use positive deltas to store the deltas between successive locations in the lists, and that gets you a great deal of compression. Instead of having to store a 64-bit integer as 8 bytes, on average you can take 2 bytes for it, which is a great saving. And that translates directly into performance. By doing that, if you create what I would call a full text index, by which I mean every word has been indexed in, every, say, English word has been indexed in its location, so that by inverting the inverted file, you could get back to a representation of the text which merely would not have white space correctly and has perhaps lost punctuation, then your index will be about 30% of the original size of the text. If you're prepared to throw away the ability to do phrase queries, in which case you don't need to know where a word occurs within the document, you just need to know that it's within the same document as another word, then you'd put every single document at one location in the index. All the words in that document fall at the same location. If you do that, your index gets down to about 10% of the size of the original text. So now I'm going to go into far too much detail about the detailed structure of these inverted files. And that's because I get excited about it, and I hope you will too. So here's a mistake I made. The obvious format for the deltas in these inverted files is once you've done your delta compression, your delta takes up 2 bytes, you pack it into as few bytes as possible, and perhaps you use 1 bit in each of your bytes to tell you whether this delta continues into the next byte or not. So let's call those continuation bits. So you can see a representation here of that. This first delta has 2 bytes. You're using 7 bits in each byte, and there's 1 continuation bit saying, does the delta continue? Now, this representation doesn't actually work very well. There are 2 reasons for it. One reason is that the common delta size is 2 bytes. And if the delta size is 2 bytes, that means you'll pick up 2 of these bytes, you'll check the continuation bit at the bottom and the continuation bit on the second byte, and you'll say, ah, yes, this is a 2-byte delta, it's the common case, I'm on the fast path. And then you'll realize that one of those continuation bits is in the middle of your delta, and then you'll have to spend several instructions getting it out, which is really annoying. Another problem with this is that the key operation, as we'll see a bit later in the talk, the key operation in the indexer when you're doing a query is being able to run along a list of these locations, trying to find the first location which is at least as big as some parameter that you've been given. That's a very important operation. You do it all the time. So that means you're parsing a great many of these deltas one after another. As you're parsing them, you're having to decide, is this a 2-byte delta, a 3-byte delta, a 1-byte delta? And as a result, you're using conditional branch instructions. Now, 2 bytes is the most common size, but it only occurs 2/3 of the time. That's a really bad case for conditional branch instructions, because conditional branch instructions, if you mispredict them, you get a mispredict hit that might be perhaps a whole pipeline length or even longer, and you'll lose a lot of instructions doing that. So what you'd like to do is have a representation which allows you to scan along this list of variable-sized deltas and not take any branch prediction misses as you go. And there's a way to do that, and this format allows that, and in a little while I'll show you exactly what you do. You pack deltas into an aligned 64-bit word, and you pack all of the continuation bits associated with all of those deltas into the first byte. So it's really just rearranging the top picture into the bottom picture, moving all of these continuation bits into the first byte. And what that does is allows you to pick up all the continuation bits in one go and look it up in a table, and that's the key thing. What you do is you turn lots of branch predictions into a table lookup. And you can hide the latency of a table lookup by prefetching the load. So I'm not going to go through this little bit of alpha assembly language in too much detail, but I want to tell you a little bit about what this does. These 6 instructions pick up one delta from a 64-bit word, having got the length from a table lookup. They cut it to the right length. Then they add it to the current running total that is where you are in your delta compression or delta decompression as you're running along. So they add it in. That undoes the delta compression. They test it to make sure that you haven't passed this parameter that you've been given, the one you're searching for in your common case as you run down your list of deltas. And it sets things up to do that same operation for the next delta. It does all of this in 6 instructions, all of which can be made to dual issue on a dual issue processor and quad issue on a quad issue processor. Other nice properties that it has is that in 6 instructions, exactly 3 of the instructions use the barrel shifters. So if half of your execution units have barrel shifters, which is the case in all the processors that I deal with, it will still quad and dual issue. And it has the property that the only branch prediction miss you will ever take is the one that says the loop has terminated. The result of this is that you can write 35 instructions to completely process a 64-bit word and every delta in it. And you can make those 35 instructions issue in 10 cycles. Just in case you doubt me and you're incredibly good at reading alpha assembly language, I have them here. I'm not going to tell you exactly what's going on here because it will bore you, but I want to tell you a couple of things just to give you the impression that RISC machines did not make assembly language programming that much easier if you really want the last ounce of performance from your machine. One of the things you'll notice about this is these comments that run down the right-hand side. These comments are comments to me to tell me which of the 4 execution units on this processor that instruction is going to execute in. If you try and let the processor decide that and you don't try and fix it yourself, it will run much too slowly. You'll notice that some of the instructions are indented. That's because this particular processor is in 2 halves. And it's so wide and the clock is so fast that it takes an extra cycle for a result generated by an add instruction, say, in one half of the chip to reach the other half. So you have to know in which half of the chip your results are going to be generated if you want to use the result in the very next cycle. So you have to do all that to get the right answer.
So did you try just writing source code and setting through a very aggressive rescaling kind of compiler and see what you got?
I believe that there is at least a factor of 20 difference between compiling this from C and writing it in this assembly language.
What are the main problems with compiling code? Was it bad?
Branch prediction is a major problem. If I had not got rid of all the branch prediction misses, this code would run approximately 3 times slower. Branch prediction miss on this particular processor is quite awful. Another issue is that it's very hard to imagine an optimizer being able to make some of the optimizations that were made here. For example, I found that I was using too much, I was using the barrel shifters too much. I had to change a basic data structure in order to avoid doing that, and an optimizer is not going to be able to do that.
So if you change the basic data structure and rewritten it in C, would an optimizer be able to, and given profile data, would an optimizer be able to?
Not a hope. I wouldn't believe it for an instant, which is great news for me. I had worried that optimizing compilers and very large numbers of transistors would take this fun away from me. I should have told you my motto before I started, which is that there is no project which cannot be made more fun by over-optimizing. The really cool thing about this was that while working on this particular project when AltaVista came along, was that I discovered that I was in this wonderful position where by improving the performance of this loop by 5%, I could pay my salary for a year. And so it was easy to justify. So that's enough about the inner loop. Now I'm going to tell you something about something significantly more high level in the indexer. This is an interface it allows you to build up queries. It's an interface for reading the result of a query as an ascending sequence of locations. So one way to think about this is as an interface for reading that list of locations out of the inverted file. But it's much more general than that. These things are actually objects, so they have methods. Of course, this is all programmed in C, so the objects are all done by hand. But there's one basic implementation of this at the bottom, which reads these locations out of the file from this delta compressed list. And there are other implementations which do operations like OR and NOT and things like that. And we'll see how to compose them later. But let me tell you about the interface a little and what was so nice about it. So in the interface, there's a call lock which reads the current location. These things are like streams, so you're reading from this list of ascending locations. At any time, you can call lock, and it will tell you the current location. You can also call next, and it will advance the location, that is, move on to the next location in the list, which is bound to be higher than the last one, or it will tell you that it's reached the end. There's an operation called seek, which takes a parameter, x, and it advances the stream until the current location is at least as big as x. You'll remember that's the operation that I told you was the key operation that you need to do fast on that previous data structure. Perhaps it'll become clear why you need to do that operation a lot. There's one subtype of this data type which adds a method called prev. That allows you to peek backwards one location and see what the previous location was. It doesn't actually move the stream backwards, it just lets you peek backwards without moving it. There are no methods that move the stream backwards. That prev operation is used for fielded queries. Now you might wonder why I had a subtype. Why didn't I just implement the prev method on all of the objects? Well, the reason is you can't do it efficiently. One of the really nice things about this particular interface was that I discovered that you need the prev method to do fielded queries. So you need it sometimes. But you can't implement it on some of the implementations of this interface. And it turned out that exactly the places where you could implement it are where you need it, and exactly the places where you can't implement it are exactly the places where you don't need it, which was just wonderful. And I wouldn't have been able to predict that. So here are some of the implementations of index stream readers. There's the file implementation. That's the base level one. That reads the data structure I was talking about before, the actual inverted file. So the seek method of that implementation is exactly that inner loop, which I showed you some of the instructions of. And so it's going to be running along, undoing that delta compression out of the inner loop and looking for the first location that's at least as big as the parameter. The OR implementation of this thing merges two or more streams. So that, since these things are just monotonically increasing lists of numbers, it's just a straight merge sort operation. There's nothing complicated about that. NOT returns all of the locations from the potential location space that are not in the stream that's the argument. Since this is a 64-bit space, you can see why it's important that these things are lazily evaluated. There's a very complicated implementation called AND, which I'm going to, in the next few slides, talk a little bit more about. And it contains a constraint solver that allows you to construct very complicated queries. It's capable of doing AND, conjunction. It can do phrases, proximity, fielded queries, all kinds of things. And it does it with a constraint solver that has some very beautiful properties. Once you have these streams and these implementations, you can build up queries in a very natural manner. So for example, I apologize for the marsupial nature of these queries. If you wanted to do the query wombat or numbat and pouch, you could build it up by creating, first of all, these basic index stream readers which read directly from the inverted files. These are the top, one for each of the words in the query. ORing, which remember is just a merge sort, ORing the streams here to get wombat or numbat, and then using the AND ISR with some constraints which are fed in from the side to get that conjunction. And so you can build up an expression tree in just the way you might in all kinds of other things. So let me tell you a little bit about this constraint solver. So when you construct one of these objects, you give it a list of other ISRs. As you saw, there were inputs coming in at the top of that box on the previous slide. And you give it a list of constraints. There are 4 constraint types. They're all listed here. Let's talk about the first one. If A and B are index stream readers, one constraint can be that the current location of A is at, less than or equal to the current location of B plus or minus some constant k. You get to pick k. All of the other constraints have the same form, except you get to replace one or the other of both of those location operations by the prev operation, so you can peek one backwards. So all of the constraints look like this. Now, you might have thought that, wouldn't it be good to have constraints at a higher level, things that say a phrase of A and B, make A and B next to one another. So that would guarantee, for example, that the current location of one word is the current location of another word minus 1, which would mean they'd be adjacent if you'd used locations in the obvious way as words. But I didn't do that. Instead, I'm using these much lower level constraints. And the result is that if I want to find a 2-word phrase, AB, and let's say that the capital A is the ISR for the word A and capital B is the ISR for the word B, I need these 2 constraints, which together, I'm sure you can do the appropriate bit of algebra, together these insist that lock of B is equal to lock of A plus 1. Which guarantees that if the constraint solver does its job correctly, it will return all the places where there is an A and a B next to one another in your document. So you're still wondering why it is that I chose these low-level constraints instead of more high-level constraints, which might have been potentially more efficient or easier to deal with. And the answer, oops, let me put this slide up anyway. I won't give you the answer yet, sorry. Here's a bit more justification for why maybe I made the wrong decision. If you wanted to do the conjunction A and B, it takes me 4 constraints. I've introduced another ISR here. E is the ISR on the end doc word. Remember, that's the word that occurs at the end of every document in the index. With those 4 constraints, that guarantees that I found an A and a B in the same document. The first 2 constraints just say that A is between the current position of E, the end doc stream, and its previous location, which says A is in some document. The second two constraints on the second row are doing the same thing with B, but of course it's insisting that B is in the same document. So these two sets of constraints together are insisting that A and B are in the same document. So that gives you conjunction. A more complicated one, which I won't describe, is dealing with a begin title mark and an end title mark. It takes 4 constraints to say that A is in the title. So you might think I've gone overboard in these simple little constraints, and there are too many of them. But the reason for having these nice little constraints is that the solver algorithm is trivial. So those 3 lines at the top are the complete solver algorithm. Of course, all I'm doing is telling you what you have to do for correctness. If you want performance, it's a lot worse. But if you have some unsatisfied constraints, you pick some unsatisfied constraint from that set of unsatisfied constraints, and you satisfy it. And then you keep looping until you have no unsatisfied constraints, and then you have a solution. If you keep doing this, you will find every solution exactly once in monotonically increasing order. And the only hard part in that list of things I've told you how to do is, how do you satisfy a constraint? Well, in this list below, I've told you exactly what you have to do to satisfy any one of the 4 constraints. So for example, to satisfy a constraint of this top form, lock of A is less than or equal to lock of B plus or minus some constant, what can you do to satisfy that constraint if it's not satisfied? Well, I told you can't move a stream backwards. There's no method that will do it. So you cannot possibly make lock of A any smaller than it is, because you can't move A backwards. So the only thing you can do is to move B forwards. Well, how much should you move B forward? Well, obviously, you have to move it forward to at least lock of A minus K. How do you do that? Well, the seek method does exactly what you want. That's why it's there. That's why, of course, the seek method is the thing you're calling all the time from this constraint solver. You're spending all the time running around that loop calling the seek method on all the various things. Very similar algorithms can be used for all the other 3 different types of constraints that this constraint solver needs to deal with. So the result is that with a very trivial algorithm, you can get correctness from this constraint solver without having to think too hard. Whereas if you had constraints of the form, this is a phrase, or this is in the title, and then you filled in the things, the solver algorithm would become unmanageable fairly quickly. Now, of course, one thing I'm not telling you in this talk is how you make this go fast. To make this go fast, it's critically important that when you pick the unsatisfied constraint that you're going to satisfy, that you pick the right one. The right one to pick is the one that will advance a stream furthest in your index. And so there are all kinds of heuristics in the code to keep track of how far things will advance if you attempt to seek on them. What it does is it keeps track of how far things advanced last time you asked them to seek, and that way it can decide that this stream is a stream of rare things or that stream is a stream of common things, and it can choose to advance the rare streams first. So, now I'm going to tell you a little bit about what happened when we started using this thing in terms of performance and a few metrics. And then I'll switch gears and start telling you about some more non-technical stuff, which goes under the title of war stories, which you might find amusing. So the whole library is about 20,000 lines of code. It indexes around 1.5 gigabytes a second per hour on a decently fast CPU. As I said, I wasn't really interested in very high performance indexing. Queries take about 100 cycles per query per megabyte of input text. That seems like a funny metric, but if you want to sort of scale it by processor, then it's hard to express it any other way. That, of course, is for a mean AltaVista query, whatever that means. The result of this is that if you take a query of the normal type that you might type to AltaVista and run it on a processor of a few hundred megahertz of an index of 100 or 200 million pages, it will take a small fraction of a second to run, which is a good thing. Queries are CPU bound. 95% of the time is spent in user space. This also is a good thing. If anyone tells you that their search engine is disk-bound, they are nuts. The reason for that is that CPUs get faster every year, and disks don't. So always buying more memory to make your search engine CPU-bound is a good thing. The memory bus is currently underutilized in the machines we have, which is good because it means we can keep plugging faster and faster processors in, at least for a while longer. If you care, here's a little breakdown of where the time goes. This is why optimizing that inner loop was so important to me. Even after doing all of that optimization, 30% of my time is still going into those instructions. And as a result, it's worth spending a lot of time optimizing them, and it saves a lot of money in hardware that you don't otherwise have to buy. Some time goes into the constraint solver. Some time goes into higher level seeking code to avoid you having to call that inner loop quite so often. Not much time goes into the ranking code. This is a very well-behaved application in terms of its use of the memory system. It does not get a huge amount of cache misses. It uses every piece of data it brings into the registers really well. So it looks incredibly well behaved, and it doesn't get any branch prediction misses to speak of either. So here are some things I think I did right. Index stream readers turned out to be a great interface. They worked really well. They just fit in naturally in exactly the way I would have wished, and nothing went wrong with them. The flat location space worked out really well too. It turns out the clients can choose to put structure on the location space themselves, and because I'm not imposing it on them, they can do all kinds of things which I never dreamed of. Representing all of the structure of the documents as words also worked out really well. We went so far as representing dates as words and date ranges as words, which means that if you look up a date range in AltaVista, the same query optimization is taking place on those date ranges as on every other word. So we didn't have to add code to this thing to handle numbers. They're all just words. There were some regrets. In hindsight, I should have made it possible to run index stream readers backwards, but I didn't. The main reason for this is that the natural way that you get the results out of this thing is in the order in which the documents appear in the index. And for some things, you'd like things to come out in reverse order. In particular, if you're building an index of, say, the Usenet news spool, you'd like the most recent things to come out first. But they're the things you added to the index last, so they'll be at the end of the index. So that's kind of irritating, but hindsight is a wonderful thing. And of course, I wish that some things, particularly that constraint solver, were less complex. You might think that it would be nice if the inner loop was less complex, but I actually enjoyed that. So now, I'm going to switch gears completely and steal from another talk which Hank thought you might like to hear about. I'm going to tell you about, oh, a question, yes. Sure, yes.
You said that 95% of your time is spent in the application and 5% in the kernel.
Yes.
I'm just curious, what is the kernel time going into? What do you do?
Well, occasionally you will take a page fault because not all of the index fits into RAM. There is an awful lot of RAM distributed about a fair number of machines, but the index is truly enormous. So occasionally when some horrible rare word gets looked at, we'll take a page fault. Also, of course, there's networking to be done. Because there's not much networking, because one of the really great things about the AltaVista application is that the queries are tiny and the results are tiny because we don't send most of them back to the user. So, this talk, when it's by itself, is called AltaVista War Stories. Let me tell you a little bit of background. I should add, by the way, that I am talking about the structure of the AltaVista site as it was perhaps a couple of years ago. Now, as you probably know, AltaVista is a separate company. I am not with that company. I am still with Compaq. I stopped working on AltaVista full-time 2 years ago, though that inner loop I showed you I did just 3 months ago, so who knows? So the site may look somewhat different from this today, but at least 2 years ago, this is what it looked like. The main work, all that stuff I was just talking about in the last talk, is done by a bunch of large alpha servers, which we call the backends. They're clustered together in groups, and each group of servers, like as shown here are 4 of them, will have a complete set of all the index files. So each one of those machines will have 1/4 of the index files and will handle 1/4 of the index. Now, of course, the groups might be bigger than that or they might be smaller, but 1/10 of the index. Those talk to an FTDI network implemented by one large switch to some front-end machines which run the HTTP servers. Those, in turn, talk to another FTDI, again implemented by one FTDI switch, to the border routers which connect out to the internet. The front-end servers are also alpha machines, but they're considerably less powerful than the machines at the back end. So these front-end machines are basically just one processor workstations, the kind of thing you might have on your desk. So for the rest of this, well, one of the things I want to do is tell you how we anticipated handling failures, hardware failures and software failures in the system. And then I'll tell you what really happened. So here's the story which we had in our minds. Suppose a disk failed. All of the disks are on RAID controllers, so the story is easy. The RAID controller fixes it. Ha. Suppose a backend fails. Well, the front ends know about all of the backends, and there are lots of different backends, and there's lots of redundancy because we have the index on multiple different groups of backend servers. So the front ends can choose to use other groups and get the information from elsewhere. So that's the story if a backend fails. Suppose a front end fails. A front end fails, that's potentially more serious because the IP addresses of the front ends are being used by web browsers out on the internet. You can't have that IP address going away. So what we do is a very simple solution. A hot spare is monitoring the IP addresses of the front ends, and if one of those machines goes away, it grabs that IP address and starts running. And if multiple front ends fail, it will grab more than one. Suppose one of those FTDI switches fails. Well, that's a really bad thing. In the system at that time, there was nothing for it but manually replacing FTDI switches, which is really bad. Basically, it was a cold standby, and you walked up to it and switched it over. It never happened. Those things don't fail, so I'm not actually going to complain about that. One thing I didn't mention on this picture back here is there are actually 2 sites here. There's this link here going to an alternate site. Suppose an entire site goes down, which is not beyond the realm of possibility because we're in California after all. The other site is on the other side of a fault line. It's also far enough away that if there was a fire, the other one almost certainly would not catch fire. But it's close enough that you can get there in a car in the same day, which is important for your operations staff. So the story there is if your entire site fails, you get to your primary DNS somehow, and you flip over the IP addresses so that after the DNS timeout, everyone's talking to your other site. And you don't worry too much about the DNS timeout being a little long because after all, this is a site failure. It's a big deal. So that's the story and what should have happened. And now, mixed in with a whole bunch of other stuff, I'm going to tell you what really happens. RAID. If a disk fails, what really happens is that the RAID controller reconstructs the disk. And many of your disk accesses, it will have to do reconstruction on as well because those will be going to the failed disk. The performance loss when you do this, if you're running your disks at anything close to their peak performance, is such that your machine might as well be dead. Actually, what happens is, or what happened, I should say, is that when a disk would fail, the front ends would look at the performance they were getting from that particular back end and declare it dead because its performance was too bad to be useful. Yes? Sorry?
What were you running for RAID?
RAID 5, implemented either by HSC 40s or by, unfortunately, a RAID controller whose name I can't remember, made by Milex, I believe. Yes, KZPSC, that would be the one. Yes. The KZPSC turned out to be much harder to configure, very much so on a turbo laser, which could not support the operating system needed to configure it, so it had to be configured on another machine and then swapped. It did not, however, have the problem that the HSC 40 had, which was that the batteries kept failing. One of the things that was bad about the KZPSC is the third point there, which is that if you have hundreds and hundreds of disks, and we had about 80 RAID controllers, to give you an idea of the number of disks at that time, you have to expect disks to fail every week. They will. Your operations staff have to check them every week. Now, you can go to the 2 machine rooms and walk down the racks looking for the little red lights and pulling them out, but it's much nicer if you can tell your operations staff to sit at their desk and the reports will come to them. Unfortunately, with this particular RAID device, the only easy way that was provided to look to see whether the disks had failed was a horrible GUI, which was hard to use because we couldn't use it through the firewall easily. And the GUI would insist on displaying as one RAID string at a time. And so you'd sit there clicking through hundreds of these screenfuls of information trying to find the failed disks. And of course, the operations staff did not do this. And I had to do it, and then I would tell the operations staff. And this was very frustrating. And of course, the penalty for failing to do it is that a machine goes down every so often. Another thing that was interesting is that when you have this many disks, you get really weird disk errors every so often. They're not very common, but they do happen. We had a disk that had the following property. You'd say, write this sector, and it would say, yes, sir, I did that. And then you'd say, read some sector, and it would say, yes, sir, I did that. And the data is A. This corrupts a file system in milliseconds. Another thing that happened to us was just Murphy. On the very first day, 14th of December 1995, the very first day we were on the internet, the only non-RAID device in the entire system that we had, which was the root disk on our one server at that time, failed minutes before this thing was unveiled for journalists. Okay. I'll tell you a little bit about file systems. When you have 300, 400 gigabyte file systems, you need a file system with a write-ahead log. Trying to use FSCK on a file system that big will take hours. It is a disaster. Every so often, some software or memory error will destroy your file system. You might think that you can take tape backups. You are wrong. When you have this much data, when you read back the tapes, they will not read, even on the same tape drive, because there will be too many tapes, there will be an error. The only way to get it back from tape is to write every tape twice. So what we did was we bought enough spinning disks that we could put the index many times all over the place, so we could always get it back from a spinning disk. The other thing about tapes is that they are too slow. Getting something back by tomorrow morning is not good enough. You need it back in 2 hours. So having things on disk is a good thing. Disks are cheap. Yeah?
You just bring down the size of your file systems. Is there something that required such a large?
The indexes, there's a lot of data here. So you really wanted large file systems. This is a big index.
What does big mean?
Hundreds of gigabytes. Split up into smaller pieces, of course, but they're quite big. These problems became even more acute when it was decided that we were going to mirror this site in various parts of the world. And remember, where do you put a mirror? You put it in a place where the internet bandwidth to your main site is poor. And so you start thinking about, well, how can we get the data there? Well, it would cost too much to actually set up a network connection, so let's send tapes. And then you think about how many tapes you have to write, and the fact that you're now reading the tapes on the drive you didn't write them on, And so you have to write them twice to make sure they'll read back, and it quickly turns into a nightmare. A little bit about those back-end servers. There's things called the Turbo Laser, the 8400, DEC's biggest machine at the time. One amusing thing about them is that the way these are constructed is they have these huge cards with large connectors on the back. There are gazillions of pins on these connectors. But an interesting design choice that was made in this machine was that the pins are on the back plane and the sockets are on the cards. So you're inserting this thing into the back plane, and you get it slightly off, and you bend a pin. And you pull it out, and you realize, I've got to fix that pin. And it's way back inside the machine, and you can't reach it, and you can't even see it because it's dark in there. So when field service would come out, the conversation would be something like this. We need field service person X. He's not free. We'll send you someone else. No, we need X. He knows how to do turbo lasers. It's very important. As I mentioned before in the discussion about RAID, the turbo laser couldn't actually, at the time, run NT. The setup software for the RAID controller ran on NT. So we had to set up the RAID controllers on one machine and move them across. It was a pain in the neck. One great thing about turbo lasers was those of you who remember old VAXs will remember what Control P did on the console. It gave you a console prompt, no matter what. That is excellent. If you want to do remote management of the machine, you need a machine that does that. Anything else is not worth thinking about. Let me tell you about the front ends. So these basically worked. HTTP service is really easy. You don't need very many CPU cycles. You can just throw ordinary workstations at the problem, and it's no problem. So our biggest problems were poorly tested software and operator error. Automatic restart mainly dealt with the former, and also beating up the people who changed the software. The IP failover scheme, which I mentioned, deals with the latter. If the main problem is that if there's a problem with the front end, the operator is quite likely to take down the wrong machine. But if you have automatic failover and hot spare is going to take care of it a few seconds later, it's not too big a deal. A little bit about the HTTP server. We started off, remember this was 1995, with the NCSA HTTPD, which is abysmal. It called the fork system call to create a new address space for every single page that it generated. It did synchronous name resolution, not because of the incoming client IP address, not because it actually needed this information, but because it wanted to write it to a statistics log. When the logging disk became full, it would continue to write things to the logging disk. And if you know what that's like on a Unix system, you'll know that that makes the machine unusable very quickly. And the other main problem with it, apart from all of the other things, was that it's prone to denial of service attacks. And I don't know of any HTTP server that you can just go out and get that deals with this problem. But it became clear very early on, like within 2 weeks of AltaVista going live in 1995, that we needed to do something both about the performance and the denial of service problem because we were getting attacked regularly. So I wrote a new HTTP server. It never forks. Everything is done with multiple threads. This does aggravate all the software test issues because it means that every time someone wants to put what would be a CGI bin program into your site, it's now a set of subroutines that get linked in with your address space. If they make a mistake, your HTTP server crashes. That was a great burden on the testing and quality assurance side, but it seemed to be necessary to get the performance that we wanted. I didn't have too much problem with it, but I did have to beat up some other programmers to do the testing. I did put a great deal of effort into denial of service issues. It's actually quite straightforward once you realize what you need to do. For each subnet, where I think of a subnet as being a block of 256 IP addresses, you keep track of how many sockets that subnet has open to you. You keep track of how many threads you have working on behalf of that subnet, and you keep track of the request rate that that subnet is imposing on you. And and you have a limit for that subnet on each of those three things. And if ever that subnet exceeds the limit, you bring it back into line. If it exceeds the request rate, you start calling sleep in its threads. And so that it won't be able to exceed the request rate because you're just slowing it down. If, when you get up to the thread limit, you simply avoid forking more threads for that subnet. So if another request comes in for that subnet, you delay that request, don't give a thread to it until one of the other threads associated with that subnet is finished. And if the socket limit for a subnet is reached, you simply close new incoming connections. And that ultimately means you're denying service to the user. A question?
What a subnet was?
It's just an aligned block of 256 IP addresses. So think of it as a Class C subnet. But we applied that uniformly across the whole thing. There's a default subnet limit for every subnet, but you can set different subnet limits for particular subnets. In particular, the subnets of AOL are almost certain to be favored because it's very likely that they will need many more sockets and threads and a higher request rate than anyone else. Someone who's attacked you is likely to have a 0 socket limit or whatever. Or if you are suspicious of someone, you might lower their threshold so that you'll see a potential attack that comes later much more quickly. All that stuff to do with denial of service attacks saved us a great deal later because this was an ongoing problem. Site defense took up months of my time. A little bit about how load balancing is done in the site. The front ends are balanced just by using DNS round robin. It turns out that when you have enough requests, it's easy to get good load balance because almost anything that is moderately fair will do okay. So they're balanced within 1% just by using DNS round robin. Once you've got control of the request, you've got it into a front end, of course, you can do a much nicer algorithm. The front ends monitor what the back ends are doing, and they use user response time to gauge the load of the back ends, and they spread the load across them. They group similar queries on particular back ends to get good caching. So that means that if one user does a query about wombats, and another user somewhere else in the world does a query also about wombats, the front ends will probably detect this and send both queries to the same back end, and so they'll get cache hits on the index files. You don't get so many page faults. And that is worth a significant performance boost. Yes?
So the front ends were actually sharing a lot of state between them?
No, the front ends are not sharing state.
So how do you know if the queries go to 2 different front ends? How do they figure out that you send it to the same backend?
The front ends are using the same algorithms. That's all there is to it. Okay. Another important thing to think about when designing a system like this is what to do when you get overloaded, because it will happen. And the really important thing to remember is not to get positive feedback when it happens, but to get negative feedback. So you need to take shortcuts when you get overloaded so that you take fewer CPU cycles and you get out of the overload state. The backends take shortcuts when they get overloaded. In particular, they decide not to give you precise counts. And then they decide to cheat on how much of the index they've looked up. And the quality of the results you get gets worse and worse until finally they have to refuse service. But because they can take shortcuts and still give some useful response, it degrades gracefully, which is a lot better than it might be. The front ends, you have to be much more careful. Because if a front end stops giving service, that's like the dial tone going away in your telephone. The front end is the thing talking directly to the browser. You can't even get an error message back to the user unless the front end can talk to him. So our response to that was to put enormous spare capacity at the front ends in order to be able to tolerate almost any attack that we could imagine. We used the same approach to, for example, deal with the TCP SYN attack, if you're familiar with that. All we did was we put so much memory into those machines that we cannot believe that anyone would be able to flood us with enough TCP SYN packets to cause us to run out of memory. Remember that the front ends are just cheap workstations, so it's easy to do that by just throwing money at the problem. Yes?
On your architecture, did the user ever talk to the backend, or was data always passed through the front ends?
Must always pass through the front ends. There is no IP route. There is not even a router that will allow them to get to that back-end FTDI network. It's not connected to the internet. One page about spammers. So, as soon as we added a service that allows users to submit pages to AltaVista, spammers started submitting a lot of pages. And the obvious thing to do was to add the same kind of denial of service mechanisms that I spoke about for the HTTP server. So the add URL mechanism keeps track for each subnet, not only of who's submitting the page, but where the page is that is being submitted, of how many pages have been submitted, how many bytes have been submitted, that kind of thing. And it limits those numbers for each day, so you can't submit too many things. The subnet limits can be adjusted, so some particular site that has GeoCities with a large number of pages, you want to be able to submit a large number of pages because there are many people there. But some random site that you've never heard of wouldn't be able to submit so many. And of course, if you've been attacked from somewhere, you set its limits to 0 or whatever. One thing that was interesting was that there's a question of what you do if you find 2 pages which score the same in your ranking function, and one of them is more recent than another. And at first I thought we should put the more recent page higher in the ranking function so it comes out nearer the top. Big mistake. Because what happens is this encourages spammers to submit the same page every day so that it will be the most recent page with its particular ranking. So that decision had to be reversed in order to discourage that behavior. Another thing that happened was we found that people will submit the same page again and again and again with minor variations. So one of the things we had to do was find ways to detect duplicate pages or approximate duplicate pages. So that involved finding new algorithms to say whether one page is enough like another one that it's not worth storing the other one. And one of the things that came out of this was that we can now do this by storing a summary of a page. So for each page, we create a summary, which happens to be 48 bytes long. Given the summary of page A and the summary of page B, we can tell you in a very quick operation whether those 2 pages are similar enough that we won't bother storing one of them, which is quite a fine thing. So we have to do that comparison operation, of course, quadratically many times on the, say, 200 million pages in the index. Sure.
Are you using your own summary files, or are you using some commercial?
That summary is done in a very interesting algorithmic way, which we did, yes. It's not an English summary, it's some hash numbers.
This is the shingles.
Yes, exactly. We try to detect bogus keywords that spammers are putting in with statistics. And ultimately, if a client keeps misbehaving, we cut off all their access to the site because there's nothing else we can do.
What's a bogus keyword?
A bogus keyword is, for example, putting the phrase University of Washington on your sex site so that people looking for the University of Washington will come to your sex site, that kind of thing. One final thought. Sorry? No, I would have thought that it would be perfectly reasonable to put sex words. Sorry. So AltaVista was a success disaster. We had 2 people. There was me and Louis Monnier were the 2 people writing all the code. The hardware was always late. And I will remember 1996 very well because throughout almost all of it, the load grew at 10 to 15% a week for over a year. And every week, because the hardware was late, the software had to work and it had to be faster than it had been the week before. And it was really hard. Are there any questions?